Hi, everybody. Welcome to today's Elastic live stream on analyzing United States mortality data with the Elastic Stack. We have Brian Vest with us today. Brian, sorry, I have some feedback. Anyway, Brian is an IT veteran. He has over 20 years of experience across all areas of the field. And just this year, he started his own company called Dangerous Metrics. So I'm going to go ahead and hand things over to Brian. Really looking forward to the presentation today. And thanks so much for joining us.
Thank you. Okay, I think the presentation is mine now. So as Faith mentioned, the name of this is Analyzing the United States Mortality Data Using the Elastic Stack. So the reason for doing this is a concern I have that possibly, changes of the environment, such as pollution, any kind of waste, e-waste, things that actually grow over time with more people, could be affecting our food supply. I can't prove this, just by saying, yeah, I know that's a problem, but I wanted to research it to see if my thoughts on that, actually had any, had any validity. Is it actually a problem? I think it is. But what I figured out as I sat down and thought about how I was going to research this is, okay, where am I going to get the data? And a few other questions. So as I worked through this, I thought, well, it would make a good presentation, after getting the offer to do it from the great people at Elastic. And so I said, yeah, sure, I'll do that. And I sat down and thought about it. And then so the first thing I came up with is, what is this project? It's broken. I have down here, you can see I have it broken down into 5 sections, and those are the question, which I just explained. What am I trying to figure out? The data that I have to work with, the challenge of working with this data, the tools that I use to decode this data, or at least make it usable or turn it into an Elasticsearch format, and what is the final result of doing all this? Well, I don't have the answer yet. The result actually is having the data to actually be able to do the research inside the Elasticsearch platform. So as we go through this presentation, where we will hit all of these bullet points individually, and you'll be able to see where I'm going with this and what it's taken to get here. So let's go ahead and get over here to the question. I explained earlier when I first started the presentation exactly or not exactly, but I gave a brief overview of what I'm trying to do. But this breaks it down into the 4 actual parts of that question, and these come down to environment. The environment, it's where we live, it's where we grow our food, it's the air we breathe, it's the water we drink. Everything impacts the environment. But the question became more so is, are changes in this environment, such as pollution, e-waste, and even down to new introductions of herbicides and pesticides, are they actually having any kind of an ill effect on the environment, which could indirectly in ways impact our food supply? These questions have been asked, answers have been given out. Big universities have done the same kind of research, and they all have their own answers. But I like to look a little deeper and try to form my own answer if I can. So in the end, what I needed was a source of data, so I could take all of this information and plug it into Kibana or any kind of analytical system. I just chose Kibana and Elasticsearch because I think it's best suited for the job. But could I find any correlation between these things? So that posed the question. You look at all these things together, and you got to think somewhere something could cause problems with our food supply like this. For instance, in 1969, the Cuyahoga River, where I live in Ohio, caught on fire because of all the industrial waste that had been dumped into it. don't you think somewhere along the line that some of that may have leached into the environment, and now it's being grown with our food? Again, this is a debate that has gone on forever. I'm not saying yes or no that this is the case yet, but this whole project is to see if I can find my own answer to this question, and if it agrees what we are hearing from science and the big universities and the big companies when this question is asked. So to answer this question, we need data. We need a lot of data to answer this question. And the Center for Disease Control actually provides this data. And you can go to their site and use their system called the CDC Wonder System to decode this data, or at least try to get your own, create your own report. The issue I ran into is this is what you see in this image is one page of designing your own report at the CDC system. It could take you an hour just to generate one report. Unfortunately, if you generate the wrong report, you can frequently get back a result that says too many results. We can't display your data. And even if you do get anything back, generally it's a single line chart or a single bar chart. And that's after spending half an hour to an hour filling out this form. Now, granted, you can select, some parts are defaulted. You can select certain things and just click search at any level. But it's still, in my opinion, I thought I could do a much better job using Elasticsearch and Kibana to do the same thing, because you can just do it faster. And we will actually see that at the end when we go to the actual public site where this runs, which I'll explain as we get into the other parts of the system. So anyway, the data is there. Their interface is no good for me. It may be good for others, but for me, it just wasn't going to do what I wanted it to do. So I started looking for the raw data. And I found the raw data. And unfortunately, it looks like this, the image that is on the screen. That is a screen capture of me looking at the very top, I think top 10 records. Since it is so small and there's so much data there, let's go ahead and go to the next slide where you can see a bigger version of it. As you can see, it's just a bunch of tab delimited numbers and letters, nothing else. Now, I happen to know that right there in the 8th block where it says 1999, that's the year. But that's only because I've been working with the data for over a year now. So that's what the data looks like. They don't make it easy to work with. So now, not that I'm saying they did this on purpose. It's probably some kind of a specification that they've been using for years. It's stored in a tape format, which we'll talk about in a minute. But maybe it works with their systems, but it's not very compatible with other systems. So that's another part of this project, of course, is to make it compatible with Elasticsearch. So then we get on to, okay, there's two ways to download this data. You can use HTTP, or believe it or not, they're actually still available on FTP. The government actually provides a lot of the public access data through FTP. And I prefer that for one reason mainly is if you use HTTP, you're going to have to keep track of what you've downloaded yourself. There may be tools to get around that, but if you just take a standard browser and go download a file, you're going to have to keep track of all that yourself. In FTP specific clients, I use LFTP, allow you to run in a mirrored mode. The mirrored mode will allow you to go back in and just say mirror, and then it will go through the whole list of files at the FTP and only download new files, which makes it much easier for doing updates instead of trying to keep track in a spreadsheet or whatever what you've already downloaded. So I use the FTP to do this. Now we get into, as I mentioned earlier, we actually have to decode this tape data. And that's why I included this image of having to run up many flights of stairs, because that's about how difficult it can be to decode this information until you get a handle on it. But with the right tools, and Elasticsearch and Kibana as the analytics engine part of this, it was difficult, and sort of difficult, and I still don't have all of the data decoded. But it was a challenge, and I like a challenge. So that's where we're at with that. But now let's hop over to Oh, I forgot I put this slide. This is one more to show you what we'll actually be working with as we start going through the tool section. This is all tab delimited, and every single one of these positions identifies to a position on a tape sector. When I first looked at this, I thought we quit using tapes in the 60s, but anyway, that's the way it is, and that's what we have to decode to be able to work with this data. So, as I mentioned in the previous slide before the last one, there's a challenge here. The challenge is all of these things listed here, which we'll go over in point. And the first one is all of the data sets have different names. This is a directory listing of my data processing server for this project. And as you can see, the files don't have the same name format. They don't have the same extension format. They don't have, there's no consensus here of how this data looks. And just because one file has the same extension as another file does not necessarily mean those two files have a compatible data set. This is the mess that you're given to work with if you download it all from the FTP. I call it a mess, but I don't know. I can't think of any other word for it. I mean, there's no uniformity here at all. It drives me crazy. Which is another reason to get it all into one format. That way, at some point, it can be exported in a JSON format and be unique and be not unique, but be the same across the board if other people wanted to work with it. That's further down the road. I don't even have half of these decoded yet because of those changes. But they will be eventually, and then I do fully plan to export the whole thing in JSON. So on top of all the data sets having different names, the data sets also have different formats. This may look very similar to what we were looking at in the 1999 data set that we've seen in a previous slide, but this is actually the 1969 data set. And as you can see, though it looks very similar, it's not, because the tabbing is different. And this is all numbers, there's no letters. This whole system of CDC data uses what are called ICD codes to decode the causes of mortality. Before, I think, 1980, they were all numbers. There were no letters involved. So this is a totally different data set to format, or totally different data packet to format, even though it's part of the same master set of data. And this is the things that I'm trying to make more uniform so other people could ingest them and use them for their own needs. But on the next section, the data format is quite obscure. As I mentioned, this is a tape format. So I know this, you can't read this. The point is not actually to read it. It's to show that this is 9 pages of a 123-page document that does nothing except tell you how to decode a tape format. Now, the problem with decoding this is a screenshotted PDF. There's no text that you could pull out of it. So this whole dictionary had to be typed in by hand. So what I'm going to do real quick is I'm going to hop over to another window where I have actually have this on the GitHub where some of this stuff is available. And it is right here. I can't make that the primary. Just a second. I have had a technical difficulty here. Okay. Sorry about the delay. I'm new to this system. I don't know how to tell if anybody can actually see the new screen that I shared. Thank you. Thank you very much. Okay, so with that little delay out of the way, sorry about that. I will get used to this machine. This is what is decoded, manually decoded from the tape location PDF file. And as you can see, there's a whole lot of data here. This has to be prepared before I could even attempt to decode this data, because it tells what every section of that piece of file means, or that line in the data file means. So you can see, if you get all the way down through here, there are up to 440 different tape positions. And really, to make any kind of a solid report, you have to have all of this. One of the funny things, well, it wasn't funny when I ran into it, but it's funny now, is when you have the state of occurrence or state of anything, you have to have these values that are the values of the state numbers, like 01 is Alabama. Well, as you go through this set, 01 is not always Alabama. Alabama is sometimes 00. Sometimes states near the bottom of the list, like the Northern Marianas or Guam, are not these numbers. They're different numbers. I never could find out a reason why it was that way. But again, that's how vigilant you have to be on making sure that your data is completely correct. I could have made the mistake of just copying the state list from every single tape position and saying this is always going to be it. But if you make that mistake, then your data is worthless. You have to verify every single piece of data that you're going to pull into this dictionary. And that's for every data project. You definitely need to verify your data, especially your static dictionaries, or your data is worthless. And you may not even know it, and you may be giving bad data. Just, check your data 5 times, check your data 20 times, especially the static dictionaries that you have to use. Because there's a lot of data there, and one little mistake can skew all your results, and then it don't look so good in the future when you come out with other projects either. So with that out of the way, I'm going to hop back to the slides now. Again, this dictionary, and then an older version of the Perl script that does the ingesting, is available at the GitHub link that is at the beginning, and at the end, it will be at the end of this presentation. So you can go download the dictionary and look at it if you want to. Download the Perl script to maybe get some ideas for your own script that you want to do, or modifications you want to make to it. But it's all there. The Perl script's pretty crude because it was revision 1. Pretty soon I will be uploading the most recent version, which is a little faster and more compact than what's there now. So now I am switching back to the slide, the presentation. So we're going to share screen, and back to here. Thank you. So we went through here the data format being quite obscure. And it being a 123-page document to do nothing but decode that tape file, which you saw in the GitHub that I scrolled through quickly. So then we have to deal with the dictionaries being in multiple formats. Now, what you saw on GitHub was just the dictionary to decode sections on the tape. That's nothing more than to say this key belongs to this section. But when you get down into the access codes, the actual causes of mortality, well, that's 2 different dictionaries called the ICD-9 and the ICD-10, depending on what year of data you're working with. Those dictionaries look like this. What you see on the right of the presentation slide. Each of these numbers and sub numbers are different types of. Generally, the whole numbers are primary categories, and any well, you could call it a float, but technically it's not because there's zeros in the front. But anyway, are subcategories. There are something around the neighborhood of 12 to 1300 different codes that can be used to mark the mortality and the causes leading up to the mortality. Luckily, these are in text and XLS format, so I don't really have to create static dictionaries out of them. The Perl script reads them in on the fly and creates its dictionaries as it needs. Generally, in Perl, this is called, they're stored in a hash, what we call a hash, but in Node, or actually JavaScript or most other languages like Python, it's called an associative array. But for me, hash works fine because I used Perl. And then pretty much it all comes in little paper pamphlets like this that have been scanned into PDFs, which is why I mentioned before that you can't, unlike a text file, since these were scanned, or even a PDF that was actually typed, you can use modules to go in and pull all the text out. Unfortunately, these are scanned, and that's why the one dictionary had to be completely typed by hand. And again, even though, I spent the time typing it, I have no problem giving it away for other people that want to look at it. And that's why it's up at the GitHub repo here, mainly because, I think everybody deserves access to this information. Everybody deserves an easier way to use it. And if I do all the work and then keep it to myself, well, then what good is that? So the final output, well, actually, I got ahead of myself. This is a more compressed version of the tape location dictionary that we saw at GitHub. This just has all of the secondary keys compressed. But as a note, if you look at that file, location, everything from 0 to 345 are all static data, pretty much. Not really static data, but data that is always going to be in the same place. So I guess that still would be static data. These down here hold the axis conditions, and they can be different and all over the place. So I decided to bring them out into their own keys and keep location under here, just so I can identify what are the static locations and what are axis locations. It's easier for me. It's easier for the script. But what we finally want to get to is a nice, pretty JSON output that looks like this, JSON. This is actually a screen cap from a Kibana Discover, window with the data being shown in JSON mode. This is one record for one death in the United States for one day, one person. All that data. Now, some of these are null fields, and that's to be expected, especially when you get down to the axis conditions, because you've got 14 axis conditions. You don't always need 14 places to decide, or to put in what led up to the death. Or some of them are 2 or 3. Some of them, I've seen a few that use 14, but not many. So with the challenge presented, then we have to decide what tools will best suit the job. Well, number one is Elasticsearch. I have used Elasticsearch for a long time. I like to throw a little story in whenever I'm talking about my love for Elasticsearch. I'll compress it since we're on a presentation time limit. But I first was really deeply introduced into Elasticsearch around version 5.6. I was a server administrator at an ISP. I had a mail problem running through the systems that I couldn't figure out. It was just this lag that would come and go. It's sometimes slowing mail down for 15, 20 minutes or longer, depending on how high the load was. And I just couldn't track it down. And the mail system generated 3.5 million log entries a day. So, trying to search that with your standard Linux search tools like grep was near impossible. So I run up on Logstash, which of course led me to Elasticsearch, which led me to Kibana. I did the work, figured out the filters, plugged the mail logs into it. And after getting all that done, it only took about 3 days to figure out that the lag, the reason it seemed phantom to us was because it was being caused by external block lists. And because it seemed phantom to us, it wasn't happening inside our infrastructure. It was the delay to get a response from the block list servers. So when they would have problems, we would have problems. So that was my first introduction, and where it was so easy to get the logs going, to write the filters in Logstash, and then build the dashboards in Kibana. Now it becomes my go-to for any kind of analytics I need for any kind of system. And I'm really good with it. So I like it a lot for that matter too. So the screen over here you see real quick is my home lab. Actually, if you see me in the video, I don't know if you do, but this server actually runs right here in my office. It's got the flashing color fan lights the back there. Yeah, you can sort of see it, but yeah, so it's sort of behind that cup of pencils, and you can see the flashing light. So yeah, there it is. That is pretty much where this whole project runs right now, even the part that is able to that you'll be able to see at dangermetrics.org. It all gets piped from here, and we'll go through that in a minute as we get further on in the tools. So this specific cluster is all running, all the nodes are running on one ES6i host. And in a minute, I'll tell you why that's not a good idea. But for this project, it's a fine idea. It works okay. I've got my data backed up elsewhere, and I can always run the scripts to repopulate the servers if needed, or repopulate the nodes. But anyway, this server, each of these nodes runs 4 cores carved off of a AMD Threadripper. They all have 12 gigabytes of RAM, with 6 of that dedicated to heap. They all have 600 gigabytes of storage for many different projects that I work on at the same time, which are probably 10 besides this one. And currently, you can see under the documents count, it's serving almost 500 million documents just from this one little server, and it does quite a fine job doing that. Of course, my search load isn't super heavy, but otherwise it does just a fine job with just that. Of course, Kibana is the analytic, head in for Elasticsearch. It does a lot of things really well. Actually, everything I've ever needed to do with any kind of analytics, Kibana has done everything I've needed to do. It's I don't know. It's just the ease of use, and just how easily it now, especially now in the later versions, plugs into Elastic without many issues. Just makes it really my go-to interface. Another part of this project, which is what allows everyone to actually, which allows people to access this through the domain dangerousmetrics.org, is Nginx. Nginx runs on the external host, and it just really just does a reverse proxy in the HTTPS handshaking and sits in front of Kibana. So and it's not that I have a problem with Kibana and the way it does security and the way it does HTTPS. It handles its authentication just fine. I have no problems with that at all. But since I use Let's Encrypt and CertBot, it's really, in my opinion, just easier to let Nginx take care of it and then set it up as a reverse proxy in front of Kibana. That's the only reason I did that. If you've got your own certificates, and you can easily plug them into Kibana, a lot of times that's the better route to go. It really just depends on your use case and your infrastructure. But in my case, this was the best way to go with it. And now we come to Perl, the scripting language that runs all of this. Some people would say Perl's a dying language. People don't use it much anymore. I tend to disagree. I mean, there are newer tools out there. There's Python, there's JavaScript running on Node.js. But I've been programming in Perl for 15 years. So I've got a pretty good handle on it. I can write things pretty fast in Perl. And it just so happens that the way a Perl array works lines up really well with the way these tape sectors work. So I can run this command in Perl, and it splits that whole line, even including on every character, every empty space, into an array that matches the length of the string. And then I can easily easily run those array elements back together And then, as we've seen before, this is how the tape dictionary is decoded. Um, so it just makes it easier because I can then go, okay, this line 0 plus line 1 equals this location, or line 346 plus, or character 346 plus character 350 equals this condition. It was just a lot easier to slide them back together that way. And that's mainly where it clicked in my head to use Perl for this. Now, it could be done with Logstash. If you know how to do Logstash filters, it could easily do the same thing. And it could even, Logstash even supports its own dictionaries of a very similar type to this. This could all be done inside of Logstash. But for me, it was just faster to do it in Perl for this run. So that's why I chose Perl. And my data processing platform for this is Ubuntu. In my opinion, and this is an opinion, some people may agree or disagree. Linux kernel-based operating systems are just much better for heavy-duty data processing like this. Ubuntu is my distro of choice. I have spent time with Red Hat, CentOS, Straight Debian, Slack, other distros, but for some reason I just always come back to Ubuntu because that's just what I like the most. But any Linux distro would be able to do the same work because the same tools are available on those distributions. So I did a little screenshot here or a little block diagram of how all of this works. So as I mentioned, the external VM host is out here and it runs Kibana metric beat and file beat. Again, to reiterate, the Nginx reverse proxy is only here to handle HTTPS handshaking, which then it hands everything, including authentication, back off to Kibana. This connects to an HA proxy at home in the home lab, which just gives me another layer of security and metrics to monitor what's coming in across the dangerousmetrics.org domain. This is the home lab. It all run, and I spelled ESXi wrong. I figured that out after I already submitted the slides, but it's not EXSI, it's ESXi version 7. The Elasticsearch cluster completely runs inside this host. So does Kibana, HA proxy, and the data processor. Now, I mentioned earlier that this is a bad idea, and I'd like to reiterate on that. It is never a good idea to put your whole Elasticsearch cluster into one virtual host. Your data HA is out the window. All of your nodes are going to be sharing the same data bus, which is going to slow things down. Over time, you're definitely not HA. I think I already said that, but just want to reiterate that a point again. If this server were to go down, I lose all the data that's on it. In reality, it's not even good to have two nodes of the same cluster on the same virtual host, because then, unless you have custom routing in place, your HA proxy, your high availability is shot, because if you lose that, you lose two nodes, and then there's a good chance the cluster won't recover. Don't get me wrong, Elasticsearch is great for data recovery, for swapping replicas into primaries, and anything that you need to do to make your data resilient in HA. But it's still limited by the infrastructure that it's installed on. So in no way would I ever recommend installing any more than maybe 2 Elasticsearch hosts on one virtualization platform, unless you have custom routing in place to make sure those shards don't end up on the same nodes on the same host. Again, like I said, they all share the same data bus. I try to spread out the hard drive load by putting each Elasticsearch node storage on a different hard drive. But even at that, you're still bound by the speed of the SSD bus and the memory bus and everything else. But for a lab situation, this works. Really not, it don't. For my lab situation, it works. Other lab situations may even want to take some of those thoughts into consideration, because again, you can have a lab cluster full of data, and if you lose it, you're hurt. So anyway, just some things to keep in mind. I wanted to put this slide up here to show how this works and how I'm able to serve dangerousmetrics.org out of my home lab, but to let everybody know that this is not something you do in production. So with that out of the way, so this all hooks up to a Ubiquiti 24 port switch, which goes through my home network. to the internet, and then all that interaction happens between Kibana and the HA proxy on a secure port to let this Kibana host talk to this cluster. I see your question about how much data was brought in for this project. No, I have not mentioned that yet, but let me get that count for you real quick because I'm right on the server. This data set uncompressed is 43 gigabytes. So that's what it is. Now, if you download the whole FTP at CDC, such as I did, it's about 380 gigabytes. But if you just want to get the mortality data, you have to navigate to a specific folder inside the FTP. And that changes every now and then, but let me see. I don't remember, but when we wrap this up, I'll drop that information in the GitHub and in the README file, so you know where you would have to navigate to just to get this data. Because it's a great big long FTP URL like /health statistics /NCHS /DVS /dataset /something. But I'll go ahead and drop it in the README on the GitHub when this is over. So anyway, we'll hop on here to now the result, what I hope to get out of what we've gone through so far. First of all, of course, Elasticsearch ready data. And you've already seen this, but it's pretty much the data that we're trying to decode from these tapes in JSON format. All of these tools together were able to do this. And I'm really happy with the result. And again, and one thing too to note that I should have mentioned way beyond before, the Elasticsearch cluster that I'm doing this on only has the basic license. I mean, you can do basic stuff like this, even some really advanced stuff with just the basic license. Now, if I wanted to go into deeper into saying, okay, I want to automatically download the next data set that comes out and then compare it to the data sets that I already have and see if my conclusions were correct. You could do that with some ML work, some forward-looking ML work if you were using the licensed Elasticsearch. And I may do that at some point. I just don't have enough of the data decoded yet to warrant doing that. If I was going to do that, though, I think I would probably just move it into the Elastic Cloud. And if the dangerousmetrics.org website, which I'll put I actually haven't given the login info for that yet, because when you go there, you're going to be dropped directly into a Kibana login. I will also include that in the README for a GitHub really soon after this presentation is over. Then, of course, we want to use this data to build Kibana dashboards. This is a screenshot of the Kibana dashboard that I built. It doesn't show everything. It doesn't show all of the access conditions. I'm still trying to figure that out because there are 14 of them, and I don't want to clutter the screen, which is what I'm trying to avoid, like the cluttered screen if you go to the CDC tool. But it's on a note as far as how I built this uses the original Kibana aggregation type system. They're much more powerful. I think I mentioned this before, but there's much more powerful tools now like Lens and Vega and things like that. But this is what I'm accustomed to, and I can build them faster this way. So that's initially what I start with. And then the last part here, or not the last part, but the next part is one of the goals was to make this accessible to the world. It's public data. Anybody can process it. Anybody can view it. And I I just don't, I hate this thing called data siloing, where you have a bunch of data that everybody else doesn't have and you just keep it to yourself. Well, it's public data. I think the public should be able to use it. So it will forever be available there, at least as long as I can afford to keep it running there. So with that in mind, actually I went too far ahead. Let's actually hop over to that dashboard. I'm going to do that screen share now, and we'll actually click through it a little bit and see what I've ended up with through this bit of work. Well, actually, I said a bit of work, but it was actually a whole lot of work. So this is the interface. Now, if you look at the URL, this is running. This is actually running on my lab, but it's the same thing you would see if you logged in at dangermetrics.org. What you have here is this first box is the state of occurrence. This is the state where the mortality, the death happened. The second box is the state of birth. This is the state where, of course, the person was born. And then the only two boxes I have so far are the entity access conditions 1, which generally is referred to as the direct cause of death, and the access condition 2 and after are generally conditions that led up to that direct cause of death. Now, if you've seen the CDC stuff that I showed before, the CDC Wonder System, or you've been there before, you don't get this kind of information when you go there. You sort of do, but they're all in drop-down boxes. You don't have a good visual of what you're looking for. And I just think this is a much easier way to navigate through this data much more quickly. Not to mention that when I do start plugging in the dates of the environmental changes to prove or disprove my point, it's much easier to do it. Well, actually, you can't even do it at the CDC system. They're not going to let you upload data to their system, but I can upload data to my own Elasticsearch cluster all day. And then I would create another table called environmental conditions, and I would pair it with this one, and then we'll get more reports out of that. I have not done that yet, but it is one of the ultimate goals of this project. So real quickly, let's just do some filtering here and see how much power it is. So I live in Ohio, in the United States. I will select Ohio as the primary filter. It means it occurred in Ohio. Whatever the death was occurred in Ohio. And then we can see, okay, well, there's a lot of things over here, but we also have a list of states of people that were born in, but then died in Ohio. So let's just say, okay, you were born in Idaho. Well, there's only 2 there. So we have 2, and we see a malignant neoplasm of the kidney. I'm not a doctor, but I have sort of a good idea what that means. But I'm just showing it's things that you can filter on to totally pare down what you're looking for. Now, that's just filtering on state, when my ultimate goal is to look at changes in the cause of mortality. So with that, we can go over here and say, okay, we'll look at pneumonia unspecified. Now, if you look at the ICD codes, pneumonia has a great big huge list of things, and so it only shows 1100 here. But if it included everything other than unspecified, there would be many more results. That's something you have to deal with this with these access conditions. There's just so many of them, and some of them are the same thing, just different ways of explaining the same thing. And that's something I'm still working through to make this more robust. But so for now, we have the entity access condition is pneumonia unspecified. Well, we see, okay, that was 32 people in Wisconsin. Okay, so let's go ahead and filter by Wisconsin. And so now we know that in this time frame, which is 1999 to 2002, there were 32 people in Wisconsin that passed away of this condition. And then this shows you the states they were born in. That may not seem like very useful data to some, but you can also use this to tie into, okay, well, they were born here, or going back to my original idea for this project. So what were the environmental conditions here versus the environmental conditions there, so many years later? And then you can even filter it down even more by the access condition 2. And, then you can filter by Parkinson's disease. And then you have just that one report. And down here on the bottom right this actually shows all the states, and we'll get that back to a full chart here in a minute, but it shows all the states where these conditions happened. And then here is it's hard to see when we've only got one condition selected, but it's actually a stacked graph of how this condition led to that condition, led to that condition, led to that condition. It's pretty useful. And then here is the, of course, just the complete record count for that, for those filters. Again, since I have it pared down to one state and one condition, we lose a lot of that. So I'll turn it back off and you can see them repopulate. And this is a top 10 list. So you can look down here and see there's a whole lot of people that have that their problem was reported as this malignant neoplasm of the kidney. So it's just very useful in how these conditions stack with each other. So let's get rid of these filters, or actually we did get rid of all the filters. Let's go up here and do something. Let's type in anxiety, because you can search it. If you have your fields indexed correctly, you can search on anything. So we've searched on anxiety. So since we searched on it here, it's searching across all 14 of these axis conditions. So let's go to Colorado as the state of birth. And then you say, most of them were in Colorado, which is to be expected, but then there were some that were spread all over the place. But then you get over here to the axis condition 2, and you've got everything that could have led up to that, adjustment disorders, cerebral edema, congestive heart failure. Well, yeah, all of those things can lead up to anxiety. But then that's where my plugging in environmental information comes in, to where we can say, okay, well, did this increase when this happened or after this happened, or did these conditions increase after this happened or before this happened? So this is still a work in progress, but I do think it was further along far enough to go ahead and agree to do the presentation. But again, there's a lot more work to do here. I've got something along the lines of 25 or 30 years of data to import. I do have to bring in the environmental conditions. But the reason, another reason I wanted to bring it up here is it's still very useful for people that just want to do basic research of, like I said earlier, my home state is Ohio. So I can see how many people were born in Ohio and died in Ohio that had some kind of an anxiety related condition that was part of their mortality record. I did a search earlier and found, I'll try to do it again because it really caught me by surprise that it would even be listed here. But I found anxiety, which makes sense, attached to cocaine, and it was actually listed here. So since I know it was there, I can search for it. And then you've got all kinds of different options, asphyxiation, poisoning by methadone. And then if you read over here, mental and behavioral disorders due to the use of cocaine. So if we filter by that, then you can see everything that can lead up to. I mean, there's a lot of things that would tell you, don't do that. It's a bad thing. And a lot of them are listed right here. So you could come in here and type for anything. Like just a minute ago, we saw methadone. I have to get rid of this one first. And it just, you're only limited by what you can search for if you know the medical conditions. Here's poisoning by heroin, the toxic effect of ethanol, poisoning by benzodiazepines. And since we search for methadone, it actually means that these are all tied into methadone usage at some point. So it's just, even at the state that it's in right now, it's very useful for just basic research that I think is much easier to sort through than what you get at the CDC, which was that great big 3-page long, list of things that were just drop down boxes. I find it much easier to be able to see what I'm going to click on to do the filtering before having to scroll through a whole bunch of drop downs. And then doing it this way too, you see the changes on the fly. And that's one of the great things about Elasticsearch and Kibana. You see it on the fly. Like we just did. If I choose Texas, it filters everything down right away and you can see what's happening in Texas. If I choose, okay, I want to see state of birth unknown. Don't know how that happens, but it happens. And one of those, we'll see, I've already limited my methadone up here. I forgot to take out that filter. So if I take that out, then we can see that, Texas and state of birth unknown, there's 4,800 people. You can make your own guesses as to what that are, but now you can see all the reasons why they die in Texas. But anyway, that's pretty much, just the surface of what I'm trying to do here. These are, oh, I forgot to get on the race thing. It is decoded by race. And the thing is over time, race has been recoded 4 or 5 times by the CDC. There used to be many different choices, and now this is what they've limited to as of the most recent data set. So yeah, you can filter by this too. Say you just want to see white, male. And Vermont, and then it does all that filtering for you too, which is so hard to do with the system provided by the CDC. You almost would not be able to do, well, and there is no almost, you would not be able to do this with their system. You pick what you want, you go through half an hour of choosing those things, and then you get one data set returned. And like I mentioned before, sometimes there's too much data. We can't send this to you. And they also at one time offered a mapping system. They don't anymore, but that's on the roadmap for this project, is to use the Kibana maps to actually show this on a map on a dashboard also, so you can zoom into hotspots and things also. So yeah, that's that. Once I drop the login and everything into the GitHub README file, you can go poke around with it all you want. If it gets a little slow, you'll just have to forgive it, because there may be multiple people logging in after this presentation and after I posted other places. But it'll work eventually. If it gets too bad, like I said, I'll move it out to a platform with more outbound bandwidth. But otherwise, it's good just to poke around with for a little bit. Now, when I get the full data set in there, 38 gigabytes, it'll be a little more heavy, and I probably won't be able to run it from this lab server anymore. But like I said, I'll either move it to my own stack, or I'll set it up in the Elastic Cloud, depending on which looks best for me at the time. So that's the overview of the dashboard. We'll go ahead and hop back over to the final slides now. So let me get that going, and we're going to share that one. So we took a look at the resulting dashboard. I think it's pretty cool. Like I said, hopefully others will find it useful. Like I said, it'll be open to the public for as long as I have the resources to keep it open to the public. And it'll be a continuing work in progress, because as we move into the future, I will also be plugging data from the Bureau of Labor Statistics and the FDA into this platform, so it can all be tied together to find different answers for different questions, if that's what interests you. So now we're at the end. I would like to say, thank you for giving me your time to watch this presentation. I hope it was at least somewhat informative. I hope it's, if you weren't already interested in Elasticsearch, I hope it does interest you in using Elasticsearch and Kibana for future projects, because as I always say, ever since I fell in love with the Elasticsearch platform, is you're really only limited by your data and your imagination as to what you can do with the data here. On this last slide, which the slide deck is available at the invite for this presentation. So are the notes, the outline and the notes of the presentation. If you would like further information, or just want to say, hey, I like you, these slides contain my email address, my LinkedIn address, and the GitHub for this project. One last note for the GitHub for this project is it does currently have an old version of the Perl script. I will be updating that within a day or two to have a more compact, slightly faster version up there. But the version that's there does work. You will have to download your own mortality data from the CDC. That is not there. It's too big. But the dictionary that we use to decode the tape positions is there. So I think that wraps it up for me. I don't have much more to say. And again, I hope you enjoyed the presentation. Of course, there are 6 minutes if anybody has any last minute questions. I see no questions. We can dance for 5 minutes. I don't think I mentioned earlier, and since we do have a few minutes left, I don't think I mentioned earlier in the presentation that there was a time, or maybe I did, but I like effects, so I bring it up anyway, that there was a time I did work for Elastic. Very good people. I just I left to start my own business, which they were very supportive of. And this is actually the direction I plan to take that business, just finding or helping others with these obscure data sets and turning them into something that can be used. So I have no more small talk, actually. If anybody has any questions, let me know. If not, I think we can prepare to wrap this up. I think that would be up to the host, though. I do see this at the end. Thanks for saying it was exciting. I mean, I really love to get people, excited about working with data of any kind. I mean, this was a very complex data set to deal with because of the way it had to be decoded in the format that it was stored in. But again, I mean, with enough, perseverance and determination, there's really not much you can't do. Again, I'm stuck on those newer data sets because they're in a different format. But I'm pushing forward with them and expect some more progress and some more data to be added to the system within the next probably week or so. It's just the data changes so much. It's like something changes every 4 or 5 years, and it's just not compatible with the previous years. Like for instance, the 2002 data set it wasn't compatible with the 2001 data set, but that's because it was off by one character, and that's just the way the file was formatted. So yeah, that's just and interestingly, the data from the Bureau of Labor Statistics is documented and formatted perfectly. I will have no problem getting that into the system. It's clean, it's formatted perfectly. Every section has its own documentation on exactly what everything means. I wish the CDC was that way. But I guess when you're dealing with a department called the Bureau of Labor Statistics, that your statistics better be right or people are going to be mad at you. So maybe that's why it's that way. Again, though, that's all information I'll be plugging in here over time to be able to, to answer other questions and tie other things together. So, see, I guess I did have more small talk. I just thought I didn't. But that I do believe is all I have.